I want us to also pay attention to some other interesting data here. You may already noticed I listed a delta H of gas phase acid deprotonation reaction. Okay, and the reason I care about gas phase is because we know that in gas phase we don't have to worry about how your acid or your conjugate base solvate in solvent, right? We can focusing on looking at the structure of acid and conjugate base, looking at the stability of conjugate base to determine the acidity of a molecule. Okay, and also interestingly, and we're talking about ideal gas. So for each individual halogenated acetic acids, and when they deprotonate, form the corresponding acetates and the hydrogen ion, the entropy change, the delta S change for each individual acid are very similar. Under that circumstances, the delta G is only related to delta H. Okay, and under that circumstances, the delta H value essentially describes the strength of an acid. Okay, if you look at the delta H value, the fluoroacetic acid has the greatest delta H value in comparison to chloro and bromoacetic acid. It indicates that the fluoroacetic acid would corresponds to a higher pKa, or in the other word, a weaker acid. Okay, in fact, that is the case because in gas phase, the acidity is determined by the stability of the conjugate base, and the stability of the conjugate base can be is determined by two different factors. Okay, not only the electronegativity anymore, also the polarizability. Okay, so when you move from fluorine to chlorine to bromine on the periodic table, move from top to down, the polarizability increases from fluorine to bromine. Okay, and in gas phase, and the electronegativity and polarizability both play a role. Turns out the polarizability plays an even more important role, and turns out that the fluoroacetic acid becomes a weaker acid in comparison to a chloro or bromoacetic acid. So the tendency of the acidity are opposite in aqueous solution versus in the gas phase. And it's all because of under different circumstances we need to pay attention to different thermodynamic terms. Okay. Now, after discussing the reasoning associated to the acidity of different aliphatic acid in aqueous solution, we can see that, and starting with the iodoacetic acid to bromo, chloro, and fluoroacetic acid, we can see the pKa decrease, okay, from bottom to top on the periodic table. Clearly indicates that because we know from bottom to top of the periodic table, the electronegativity increase and the inductive effect for these halogens in terms of being electron withdrawing group also increase, and therefore the acidity increase. So these halogens help stabilize the conjugate base by the inductive effect and due to their high electronegativity. The inductive effect also could be accumulated, as you can see, in comparison for the chloroacetic acid to dichloroacetic acid and trichloroacetic acid, the pK value decrease, or in the other word, the acidity of the acetates increase, because these additional halogens could further stabilize the acetate, the conjugate base. Other interesting factor has to do with this number of examples of the butyric acid, okay? And as you can see, when you have a chlorine bound to the alpha versus beta versus gamma carbon, and the pKa value increase, okay, simply because the inductive effect decrease when the chemical bond increases, when the number of chemical bonds increases. So when you get to the gamma chloro butyric acid, the pKa is already quite similar to the unsaturated butyric acid. Okay.